All right, so let's imagine something pretty wild.
Okay.
Like, think about the tiniest building blocks of the universe.
Yeah.
The smallest things we know of,
Yeah.
and how they might be, like, deeply connected. Almost like twins, linked from the very beginning.
Okay.
And then imagine we take these two particles and just fling them out
Oh, wow.
in opposite directions across, like, massive cosmic distances.
Okay.
Now you being the philosopher you are, you decide, hey, I'm going to measure something about one of these particles.
Right.
Something really fundamental, like its spin.
Okay.
That's that intrinsic angular momentum they talk about.
Yeah.
And here's the kicker, the thing that even made Einstein scratch his head.
What's that?
The instant you measure the spin of one particle, it's like its distant twin instantly knows.
Oh, wow.
And it exhibits the perfectly opposite spin.
So they're linked, even though they're far apart.
Exactly. It's as if they're communicating faster than light.
That's wild.
Which, is supposed to be the universe's speed limit. And this whole scenario, it's not just some thought experiment.
No.
It's the core of what's called the EPRB experiment.
Right.
And it completely throws a wrench in our classical, neat and tidy view of reality.
It really challenges our basic intuitions about the world, doesn't it?
Absolutely. And what's even more fascinating is that these correlations, they've been experimentally confirmed over and over again.
Oh, wow.
So they're not just theoretical curiosity.
No, they're very real.
They force us to confront some really deep philosophical questions.
Yeah, like what?
Like, how can these things be so connected across such vast distances?
Right.
What does it even mean for something to be separate in the first place?
Huge questions about causality and locality.
Exactly.
Yeah.
So today we're really putting on our philosopher hats.
I like it.
And we're diving deep into this whole issue of action at a distance.
Okay.
Specifically in the quantum realm.
I'm ready.
And our guide for this journey is going to be the Stanford Encyclopedia of Philosophy.
Okay, yeah, I've heard of that.
They have a really comprehensive entry on this topic.
Sounds like a great resource.
It's like our cheat sheet to understanding all the debates and interpretations surrounding this crazy quantum entanglement.
All right, let's do it.
So let's jump right into the heart of this puzzle.
Okay.
These EPRB correlations.
Yeah.
So picture this. You've got those two entangled particles born together in a shared state and then zoomed away from each other.
Okay.
And we have these fancy devices that can measure their spin along different directions.
Right, spin detectors.
Exactly. And here's where it gets really weird.
Okay.
Even when those particles are so far apart that no signal could travel between them at the speed of light,
Yeah.
their spin measurements are still correlated.
Meaning?
Like if you measure one particle spin as up, the other one is almost guaranteed to have spin down.
Wow, so they're like linked even when they shouldn't be.
Right. And vice versa.
So it's like they're coordinating their spins even though they can't communicate.
It's almost like they're two sides of the same coin.
Yeah, I see that.
Either we think of them as separate particles.
Right.
And this is precisely what troubled Einstein, Podolsky, and Rosen.
I can imagine.
They just couldn't wrap their heads around how the measurement of one particle could instantly affect the other one.
Especially across such huge distances.
Right. It just seemed to violate everything we know about causality and the speed of light.
Yeah.
So orthodox quantum mechanics actually embraces this idea of what they call non-local influences to explain this correlation.
So what does that mean exactly?
Well, it means that the act of measuring one particle somehow triggers an immediate change in the properties of its entangled partner.
Wow. Regardless of how far apart they are.
Exactly. And this is what Einstein famously called spooky action at a distance.
I've heard that phrase before.
It just felt too weird and too counterintuitive to him.
Yeah, I could see why.
He and his colleagues believed that quantum mechanics must be missing something.
Like it's not the full story.
Exactly. They argued that the particles must possess definite properties all along, even before we measure them.
Okay.
So the measurement on one particle isn't actually changing anything about the other particle.
Okay.
It's just revealing information that was already there.
So it's more about our knowledge changing rather than the particles themselves.
Precisely. It's like if you have a pair of gloves, one left and one right,
Yeah.
and you send them to different people.
Yeah.
If one person opens their box and finds a left glove, they instantly know the other person has the right glove,
Right.
even though they didn't physically change anything about the other glove.
I get it.
It's just that their knowledge of the situation changed.
Interesting.
And this is where this idea of hidden variables comes in.
I've heard of that too, but remind me.
So the EPR view suggests that the quantum state the wave function that describes a particle.
Yeah.
It's not the whole story.
Okay.
There must be some hidden variables, some underlying properties that we just haven't discovered yet.
Oh.
And these hidden variables, they determine the outcomes of our measurements.
So the correlations we see are just the result of these shared pre-existing properties.
Exactly. It's like the gloves. They were always a pair.
Yeah.
It's just that we didn't know which glove was where until we looked.
That makes sense.
And this is what leads us to Bell's theorem.
Ah, a pivotal moment in this whole debate.
Right. In the 1960s, John Bell came up with this brilliant idea.
Yeah.
A way to test these local hidden variable theories.
Oh, wow.
And to see if they could actually explain the EPRB correlations.
So he found a way to put these ideas to the test.
Exactly. What he did was he came up with these mathematical constraints called Bell inequalities.
Right.
And these inequalities, they basically set limits on how strong the correlations could be.
Oh, interesting.
If the outcomes of our measurements were determined by local causes.
Like if there was no spooky action at a distance.
Exactly.
Okay, so what happened?
Well, quantum mechanics makes very specific predictions.
Yeah.
About the strength of these correlations.
Yeah. And in certain experimental setups, it predicts that these Bell inequalities should be violated. Meaning the correlations would be stronger than any local hidden variable theory could allow.
Wow, so it's like quantum mechanics is saying there's something more going on than just local stuff.
Precisely.
Okay, so was Bell right?
So since the 1970s, there have been tons of experiments testing these Bell inequalities. And guess what?
Right.
They have consistently shown that the inequalities are violated.
Wow. So quantum mechanics wins.
It seems so the experimental evidence really points to some form of non-locality.
Okay, so if local hidden variable theories are bound by these Bell inequalities, and the experiments show that those boundaries are broken, then we kind of have to accept that something beyond local explanations is at play.
Exactly. It suggests that the universe is fundamentally interconnected in a way that we don't fully understand.
That's pretty mind-blowing.
It really is. So let's dig a bit deeper into these local Bell models.
And see what assumptions they're making.
Yeah, what are the core ideas that are being challenged here?
So one of the key assumptions is called factorizability.
Factorizability. Okay.
And it basically means that the probability of getting certain measurement outcomes on both particles should just be the product of the probabilities of getting those outcomes individually.
So it's like assuming that the two measurements are independent events.
Exactly. It's like flipping two coins.
Yeah.
The outcome of one coin flip shouldn't affect the outcome of the other.
Right. They're separate events.
Right. But in the quantum world, with entanglement, this assumption of factorizability seems to break down.
Okay, so that's one assumption.
Right. The second one is called lambda independence.
Lambda, okay.
This one is a bit more technical.
Yeah.
But basically, lambda represents all the hidden variables that describe the state of the entangled particles when they're first created.
Okay.
And lambda independence says that these hidden variables, they're not affected by how we choose to measure the particles later on.
So our measurement choices don't influence the initial state of the particles.
Exactly. It's like saying that the past isn't influenced by the future.
Yeah, that makes sense.
Which, is a pretty fundamental assumption about causality.
Definitely. So we've got factorizability and lambda independence. And the experiments are showing that Bell's inequalities are being violated.
Right.
So which of these assumptions is more likely to be wrong?
Well, most physicists and philosophers think that lambda independence is probably still valid.
Okay.
So that leaves factorizability.
So it seems like factorizability is the one that's breaking down.
Yeah, and if factorizability is really a mathematical way of expressing locality, then it means that non-locality is a real feature of the quantum world.
All right, so we're kind of forced to accept some form of non-locality.
It seems so.
But you mentioned earlier that not all non-locality is created equal.
Right.
What different flavors are we talking about?
Well, there's a really helpful distinction made by philosopher John Jarrett.
Okay.
He talks about two conditions: parameter independence and outcome independence.
Okay, break those down for me.
So parameter independence, PI for short,
okay,
basically means that the probability of getting a certain measurement outcome on one particle shouldn't depend on how we choose to measure the other particle.
Even if they're far apart.
Exactly. If the setting of my measuring device here somehow instantly affects the probabilities of your measurement over there, then that would be a violation of parameter independence.
And that would be a problem for relativity, right?
It would seem so, because it would suggest that something is influencing things faster than light.
Yeah, like some kind of spooky action.
Exactly. Now, outcome independence OI.
Okay.
It's a bit different.
How so?
It says that the probability of a measurement outcome on one particle, given that we already know the outcome on the other particle, should be the same regardless of how we chose to measure the other particle.
So the outcomes themselves are correlated in a way that local hidden variables can't explain.
Right. It's like if the two coins always landed on opposite sides.
Yeah.
No matter how you flipped them.
Even though each individual flip seems random.
Exactly. And violating outcome independence suggests a deeper connection between the particles.
Like they're not truly separate.
Right. And this is often seen as less problematic for relativity.
Okay, so violating PI suggests action at a distance that conflicts with relativity, and violating OI suggests holism or non-separability.
Exactly, and that might be okay with relativity.
So there are different kinds of non-locality.
Right, but some physicists and philosophers think that maybe we're getting too hung up on this factorizability stuff.
Really?
Yeah, they argue that instead of focusing on the math,
we
should really be looking at the deeper ontological picture.
The nature of reality itself.
Exactly. The math is telling us something weird is going on, but the interpretations are trying to tell us what that weirdness actually means.
That makes sense from a philosophical standpoint.
Right, so let's talk about action at a distance. Holism and non-separability. And how they relate to these interpretations.
I'm ready.
So when we talk about action at a distance, what are we really talking about?
Well, the classic example is Newtonian gravity.
Right.
Two massive objects can influence each other across vast distances without anything seemingly connecting them.
Like they're pulling on each other through empty space.
Yeah, that's always been a bit of a philosophical puzzle.
Definitely. And in the quantum context with EPRB, it seems like the non-local influences between those measurements, they also don't propagate through space in a continuous way.
So it's kind of similar to gravity in that sense.
Right, but there's a key difference.
What's that?
Many argue that these quantum influences, they're not some separate force acting through space. They're more like a manifestation of this deeper holism and non-separability.
Right, because the entangled particles are not really separate. Exactly. They're part of a single interconnected system.
Even if they're spatially distant.
Precisely. And this brings us to the concept of property holism.
Okay, explain that one.
So property holism basically says that some properties of a system, they only exist at the level of the whole system. Not at the level of the individual parts.
Interesting.
Like if you have a cake. The cake has the property of being delicious. But you can't say that any individual ingredient, like the flour or the sugar, is delicious by itself.
Right. The deliciousness only emerges when you combine the ingredients.
Exactly. And in the case of entanglement, the correlation in spin, it's a property of the whole entangled system. Not a property of each individual particle.
I see.
And then there's process non-separability.
Okay, another mouthful.
This one basically means that what happens in a certain region of space-time doesn't just depend on what's happening locally at each point.
It's more holistic than that. Exactly. It's like a ripple in a pond. The shape of the ripple doesn't just depend on what's happening at each individual point on the surface.
Right. It depends on the whole pond.
Exactly. The whole process is interconnected.
Okay, so we've got property holism and process non-separability. And both of these ideas suggest that entangled particles are not truly separate.
Right, and the entangled states themselves, they also exhibit state non-separability.
Okay, so what does that mean?
Well, mathematically, you can't describe the state of the entangled pair as just a combination of the states of the individual particles.
Oh, it's interesting.
It's like the particles are fundamentally intertwined.
Even if they're far apart.
Exactly, and this state non-separability is kind of the root of all this holism and interconnectedness.
Okay, so how do these ideas of action at a distance and holism play out in different interpretations of quantum mechanics?
Right, let's start with the collapse theories.
Okay, like the Copenhagen interpretation.
Yeah, and the GRW Pearl models.
Right.
So in the Copenhagen interpretation, the act of measurement is seen as something special.
How so?
It causes the wave function to collapse.
Okay.
So imagine we measure the spin of one of our entangled particles. And we find it spin up.
Okay.
The wave function instantly changes. And the other particle is now in a definite state of spin down.
Even though they're far apart.
Exactly. It's like the measurement on one particle instantly affects the other one.
That sounds a lot like action at a distance.
It does. But, as you know, philosophers aren't always comfortable with this idea of collapse.
Yeah, what even is a measurement?
Right. And how can something change instantaneously across vast distances?
The measurement problem.
Exactly. And this is where the GRW Pearl models come in.
Okay.
They try to provide a physical mechanism for collapse.
So instead of relying on this mysterious measurement thing, they propose a more concrete process.
Right. They say that particles randomly undergo these tiny spontaneous collapses of their wave function.
Okay.
And this happens more often for larger objects.
Which explains why we don't see macroscopic objects in superpositions.
Exactly.
So it's like a more continuous and less mysterious kind of collapse.
Yeah, but even in these collapse theories, the non-local influence is still there.
Really?
When one particle collapses, the probabilities and the state of the other particle are instantly affected.
So even with a physical mechanism for collapse, the spooky action at a distance persists.
It seems so.
So does this count as action at a distance philosophically?
Well, that's a tricky question.
Yeah.
On the one hand, this influence doesn't seem to depend on distance.
Okay.
And it might even be asymmetric in time, meaning the collapse of one particle could affect the other particle backwards in time.
Oh, wow.
But if we go back to Newton and Clarke's debates about gravity, they were mostly concerned with influences between separate objects.
Okay.
And in the quantum case, the entangled particles are arguably not really separate.
Because they're linked by this non-separable state.
Right. So this leads to the distinction between strict and liberal definitions of action at a distance.
Okay, tell me more.
The strict definition says that action at a distance has to be completely independent of any other influences.
Okay.
While the liberal definition just says that it can't involve any continuous propagation through space.
So under the liberal definition, GRW Pearl models probably do involve action at a distance.
Right, because the collapse of one particle instantly influences the other particle.
Without any local mechanism connecting them.
Exactly. Okay, let's move on to Bohm's theory.
Okay, the one with the pilot wave.
Exactly. Bohm's theory says that particles always have definite positions.
Even though quantum mechanics says they don't.
Right, but their motion is guided by this wave function.
The pilot wave?
Exactly. And in this theory, spin isn't an intrinsic property of the particles.
Okay.
It's a relational property.
Meaning?
It depends on the particle's position and the wave function.
So spin emerges from the interaction between the particle and the wave?
Precisely now in the EPRB setup. The entangled state determines the form of this guiding wave.
Okay.
And when we measure one particle, it instantly changes the wave function.
Oh, wow.
And this changed wave function then affects the other particle.
Even though they're far apart?
Right, so the non-local influence isn't on the particle's position directly.
Okay.
It's on the wave that's guiding it.
Interesting.
So the measurement changes the waves, and the wave then influences the particle's disposition to have a certain spin.
So it's like an indirect influence?
Right, and this influence is instantaneous and non-local.
So it fits the liberal definition of action at a distance?
It does, but it's not the strict definition.
Why not?
Because it's not acting on the particle's intrinsic properties.
Okay.
It's acting on its dispositions.
Which are like potentialities.
Exactly. Okay, let's talk about modal interpretations now.
Okay, these are the ones where systems always have definite properties.
Right, even if the wave function doesn't tell us what they are.
So it's trying to solve the measurement problem without collapse. Exactly. And modal interpretations, they use this thing called the Schmidt decomposition.
Okay.
To figure out which properties a system actually has.
And in the EPRB scenario, this could mean that the particles have definite spins even before we measure them.
Precisely.
That's very different from the Copenhagen interpretation.
It is. So how do these modal interpretations explain the correlations then? Well, if the particles already have definite spins, then our measurements are just revealing those pre-existing values.
Okay.
And in some versions of modal interpretations, the whole process could even be deterministic. Meaning everything is predetermined.
Okay.
There's no randomness involved.
So if the particles already have opposite spins, then the measurements will just show that.
Right. And there's no need for any spooky action at a distance.
But what happens if we measure the spins along a different direction?
That's where things get a bit more complicated.
Okay.
If we measure along a different direction.
Then the particles might not have definite spins along that direction.
Okay.
So the measurement on one particle might not change the other particle's spin directly.
Okay.
But it could instantly affect its dispositions.
like its tendency to have a certain spin if we were to measure it.
Exactly. And this is similar to what happens in Bohm's theory.
Right. So modal interpretations can also have this action at a distance.
Yeah, but it's more about affecting dispositions than actual properties.
Okay. And this brings us back to property composition failure.
Right.
The idea that properties of a whole system aren't always just the sum of the properties of the parts.
Exactly. In some modal interpretations, a particle might have a definite spin by itself,
Right.
but not when it's part of an entangled pair.
So the properties depend on the context.
Right. It all comes back to this holism and non-separability.
Okay, lastly, let's touch on the Everett-like interpretations.
Like many worlds and many minds.
Right. The ones where there's no collapse.
Exactly.
So how do they deal with non-locality?
Well, in these interpretations,
Mm-hmm.
the wave function just evolves smoothly and deterministically.
Okay.
And all possible outcomes of a measurement actually happen.
But in different universes.
Exactly. So when we measure the spin of one particle, the universe splits.
Into multiple branches.
Right. And in each branch, the particles have the corresponding correlated spins.
So there's no need for any spooky action between the particles.
Right. Because they're in different universes now.
But how do we experience just one outcome then?
That's one of the big philosophical challenges for these interpretations.
Yeah, and how do probabilities work if everything happens?
Exactly. It's a whole other can of worms.
Definitely. But at least they get rid of the action at a distance problem.
In a way, yeah.
So all these interpretations, they have their own way of dealing with non-locality.
Right. Some embrace it.
Yeah.
Some try to explain it away.
And some just avoid it altogether.
Exactly. But they all have to confront this fundamental tension
between quantum mechanics and our classical intuitions about the world.
Right, so here's a big question for you, philosopher.
Shoot.
Could we actually use this quantum non-locality to send information faster than light?
That's the million-dollar question.
Right, because if we could, it would really mess with Einstein's theory of relativity.
Yeah, it would break the cosmic speed limit.
Exactly, and this is where the no-signaling theorem comes in.
Okay, tell me more.
So this theorem says that you can't use quantum entanglement to send signals faster than light.
Really? Even with all this spooky action at a distance?
It seems so.
How does that work?
Well, no matter what measurement you do on your entangled particle, you can't affect the probabilities of the outcomes that I'll measure on my particle.
In a way that would allow us to communicate.
Exactly.
Right.
So the correlations are there, but you can't control them in a way that would allow for faster than light signaling.
So it's like the universe is being sneaky.
It's like it's saying, hey, here's this weird non-local connection.
Yeah.
But you can't use it to send messages.
Okay, so that's standard quantum mechanics. But what about other interpretations or theories?
Well, the no-signaling theorem doesn't necessarily apply to them.
Oh, so there might be some loopholes.
Possibly so, in general. For superluminal signaling to be possible in these non-local models, you'd need two things.
What are they?
Controllable probabilistic dependence. Meaning you'd need to be able to control the probabilities of those distant measurement outcomes.
Okay.
And you'd need a violation of lambda distribution.
Which means?
Which means you'd need to be able to prepare the entangled particles in a way that deviates from the standard quantum predictions.
Okay, so let's look at some specific interpretations.
Right.
Can we send superluminal signals in Bohm's theory?
Well, Bohm's theory does have parameter dependence.
Right.
Meaning the setting of your measuring device can affect the trajectory of my particle.
So through that guiding wave.
Exactly.
Right.
But Bohm's theory also assumes this thing called the quantum equilibrium distribution.
Okay.
And if that distribution is fundamental, then it would prevent signaling.
How so?
Because it would average out any attempts to send a signal.
So it's like the noise would drown out the signal.
Exactly. But some people have speculated about quantum non-equilibrium states.
Where signaling might be possible?
Yeah, but those are still very theoretical.
Okay, what about modal interpretations?
Well, it depends on the specific version.
Okay.
But in general, the properties that modal interpretations talk about, they're not thought to be directly controllable.
So we can't use them to send signals?
It seems unlikely.
Okay, and finally, what about collapse theories?
Well, in those theories, the question is whether we could control the collapse process itself.
Like if we could choose when and how a particle collapses.
Exactly. And if we could, then maybe we could send a signal.
By influencing the outcome of a distant measurement?
Right, but there's no known mechanism that would allow for that kind of control.
So no signaling in collapse theories either?
It seems so.
So even with all this weirdness of quantum non-locality, it seems like relativity's speed limit is still intact.
For the most part, yeah.
It's like the universe is giving us a glimpse of this deeper interconnectedness, but it's also preventing us from exploiting it.
Maybe it's for the best.
Maybe. So it would certainly make things a lot more complicated if we could send signals faster than light.
Definitely. So let's talk about the big elephant in the room.
Which is?
How do we reconcile this quantum non-locality with Einstein's theory of relativity?
Right. They seem to be at odds with each other.
They do, but it depends on how we interpret relativity.
Okay.
Some people think that relativity forbids any kind of influence that travels faster than light.
Yeah.
While others think that it only forbids certain types of influences.
Like what?
Like sending signals or transporting energy.
Okay, so it's a matter of interpretation.
Right, and different interpretations of quantum mechanics.
Yeah.
They deal with this tension in different ways.
How so?
Well, collapse theories, they have a hard time with relativity. Because the instantaneous collapse of the wave function, it seems to require a preferred frame of reference.
Like a universal now?
Exactly. And that's not something that relativity allows for.
So it's a clash of frameworks.
Right. There have been attempts to make collapse theories more relativistic.
Like what?
Like hyperplane-dependent models or the idea of local collapse events.
Okay.
But they still have their own problems.
So what about the no-collapse interpretations?
Well, they have an easier time with relativity.
Why?
Because they don't have this instantaneous collapse.
Right.
So, for example, Evereshian interpretations, they're often seen as more compatible with relativity.
Because the wave function evolves smoothly and deterministically?
Exactly. But as we discussed earlier, they have their own challenges when it comes to explaining our experience and probabilities and modal interpretations. They've run into some no-go theorems. Meaning there are mathematical proofs that show they can't be fully compatible with relativity.
Oh, wow.
But there are newer relational versions of modal interpretations that might have a better chance
of reconciling with relativity.
Exactly. So it's still an open question.
Definitely.
And finally, we mentioned the possibility of local quantum theories.
Right. The ones that try to avoid non-locality altogether.
Exactly. What are the chances of that? Well, there have been many attempts.
Yeah.
But so far, none of them have been completely successful.
So what are some of the approaches that